Hi folks, this recording is for Algebra 1, Chapter 6, Lesson 1. We're going to be talking about solving systems by graphing. Systems of equations, especially systems of linear equations, which we're going to be talking about this chapter, are groups of linear equations. A system is a group of linear equations. Two or more linear equations together form a system. One linear equation on its own is just a linear equation. But when you say, hey, these two linear equations go together, we call them a system. All right? A solution to a system of linear equations is a point that both lines have in common. Basically, it's where the two lines intersect. So today we're going to talk about how to figure out what that point is, or if there's a point in common, or if there's many points in common, based on graphing. And you might hate it. And I can understand why, because unless you're using a computer or a graphing calculator that can do the calculations for you, graphing is kind of unreliable when you're doing it on paper or even on the iPad. And I will probably give you guys a demo on how to use GraphSciCal, which is a graphing app that you should all have on your iPad. So if you can do me a favor and pause the video and go look for GraphSciCal. It's a graphing app, and just make sure that you have it. If you don't have it, email me, because I need to make sure that you guys have it so that you can start making very reliable graphs. Okay, alrighty. So again, linear equations and systems of linear equations. We're going to solve by graphing. We're going to figure out which point both lines have in common by graphing them. So first, we're going to have two equations, or two linear equations. So my two linear equations are y equals x plus 5 and y equals negative 4x. This is a system. It is a system because I have told you that these two linear equations go together. Okay, so let's go ahead and graph them. So first, I'm going to, since they're in slope-intercept form, I'm going to use that information to help me graph, which is that the intercept is 5, which is b, and the slope is 1. And I'm going to make this line green since all the information is currently in green. So there's my slope and my intercept. I'm starting at 5 on the y-axis, and then I'm going a slope of up 1 to the right one, up 1 to the right one, up 1 to the right one. And you can also go down 1 to the left one, down 1 to the left one, down 1 to the left one. It's the exact same thing, if you remember that from a video before. I'm going to connect the dots, and I'm going to label my lines. Label your lines, especially when you're doing this on your iPad or on paper, where it's difficult to discern one line from the other. And even though I know I can figure it out, I don't want to have to spend time figuring it out. So on your tests, on your quizzes, label your lines. For every other teacher you have after me, label your lines. They will thank you for it. Okay, next line I'm going to do in this blue color. The slope is negative 4. The y-intercept is 0 because it doesn't have a b. Remember slope-intercept form from last chapter. And let's go ahead and graph it. So I start at 0, and then I'm going to go down 4, to the right 4, down to the right, to the down 4, to the right 1. Or I can go left 1, up 4, left 1, up 4. So as you can see, I actually got my lines to hit each other. The green line and the blue line overlap at one point. See where that little red dot is and the little red arrow? That is the point where the two lines intersect, and that is point negative 1, 4, which is the solution for my system. And a way you can check your point, which again, since we're graphing, your points might be off by, like a fourth or a half or even an eighth. But I don't expect you to get that crazy with how precise your graphing is. But you should be able to check your point based on your system. And that basically means plugging the point information into each line to see if you get a true statement. So I'm going to go ahead and plug this in. So y is 4, x is negative 1, which for the green line equals 4 equals negative 1 plus 5, which, hey, equals 4 equals 4. True statement, and let's try the blue line. So plug in 4 for y, negative 1 for x. Negative 4 times negative 1 is positive 4. 4 equals 4. Guess what? This is the solution for my system. Okay? That is the point where the lines intersect. It is the point which makes both of the lines' linear equations true. Okay. And don't forget to label your lines. All right. Next slide. So, oh yeah, skip that one because it's the same as the other one. I was planning to do two, but whatever. Let's move on. Okay. System of linear equations work amazingly well in the real world. If you can figure out, this is, and I'm going to get into like sidetrack for just a second. If you can figure out the trajectory of one missile, you should be able to figure out a line or a trajectory for another missile so that they hit. This is like missile defense all the way. And basically, it is something that is based on math. So if you are ever thinking about going into strategic defense, this is something that you have to know mathematically for it to make sense. If you're trying to shoot down one missile, you have to be able to figure out at what point your missile can get there to destroy it. Okay? Maybe I should have you guys make a video where you're like, hey, we've got an enemy missile and we've got like a friendly missile and we're going to try to blow up the enemy missile. Anyway, okay, so moving on. Most missiles don't move in a straight line, though they tend to move in arcs, but whatever. Okay, you are testing onto something a little bit more not war or deadly. Anyway, though if you did see the Mythbusters episode, there's one about growing bamboo through people. Anyway, moving on. You are testing two fertilizers on bamboo plants, C and D. Plant C, plant D. Plant C is 5 centimeters tall and grows at a rate of 3 centimeters per day. Plant D is 1 centimeter tall and grows at a rate of 4 centimeters per day. We're going to write a system of equations that models the height of D, or height, h of D, for each plant as a function of days. So like every day you're going to go measure each plant. You're going to see how far it has grown. You basically figure out that they have a constant growth, that every day they've grown a certain number of centimeters, okay? So plant C, its height of days, or h of D, is equal to its rate of growth times x, where x is the number of days. And actually, I should change that. This should be a D, Miss DH. There you go. Let's keep the variables constant here. Okay, so the number of days it grows times 3 is going to be how many centimeters it grows from its starting point. And basically the starting point, is the height it starts at day 0. How tall was the plant when I started my experiment? Because I don't necessarily care about the days before I started the experiment, because if I really did, I would have just started my experiment earlier, right? But since I'm starting my experiment with a plant that's already started growth, I have to take that into account. So the starting height of plant C was 5 centimeters. Then I measured every day. The rate of growth I determined to be 3 centimeters per day. All right, so that's plant C. So now let's go ahead and graph plant C. So it's starting at 5 centimeters. See, there's a little dot, see, back, dot, 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 dot. Okay, either way, and then it grows 3 centimeters per day. So after day 1, it's 3 centimeters higher than the first day, or day 0. Excuse me, that would be day 0. All right, then it grows another 3 after the next day, and another 3 after the next day, and so on and so forth. And again, this was plant C, because you have to be able to label your lines. Your lines are important. All right, plant D, and again, I need to make sure my letters stay accurate. There we go. So, yeah, there we go. All right, so plant D started off at only 1 centimeter high, but every day it grows 4 more centimeters. All right, so again, 1 centimeter is the starting height. The rate of growth is 4. So again, the rate of growth is always your slope, because that's the speed at which things are happening. And it also tells us the relationship between, obviously, the number of days of growth and how high the plant would be for that specific plant. Because, again, plant C has a different slope than plant D. Okay, so let's go ahead and graph this. So I'm starting at 1 centimeter, right. And then I am growing 4 centimeters every day. Connect the dots. And eventually they're going to end up at actually day 14. And unfortunately my graph doesn't go that high. But it does. It gets there. And then so when you connect the dots, it is going to end up at day 3 and at 14 centimeters. What the heck does this mean in relation to our original problem, though? It means that on day 3, both plants are going to have the same height. And they're both going to have the same height of 14 inches. So even though they started at different places, they had different rates of growth, they're still going to be the exact same height at one point, right? Now, by day 4, one plant's going to definitely be a little taller than the other, but they're also going to continue to grow. And there will never be another point in these plants' lives where they will be the exact same height on the same day. Okay, so again, on day 3, at 4 centimeters is when both plants will be the same height. Pretty cool, huh? Yeah, you can just visualize that bamboo growing. All right, next slide. All right, 2 friends are walking around a quarter-mile track. One person has completed 6 laps before the second person starts walking. The system is modeled below where D of t, where t is in hours, and it's time obviously, and distance is in miles. So before the second person even gets to the track, the first person has already started walking. And so we need to take that into account. Now again, if the second friend really cared about what the person was doing before they got there, they should have got there earlier, right? So we need to take that into account. So 1.5, and friend number 1 is this pink color over here, the equation on the left, right? So the 1.5 is the miles walked already. Friend 1 has already done 1.5 miles before friend 2 over here in red on the right has even got to the stinking track. Okay? Now, we know that the slope of each friend is actually how fast they're walking. It's their rate or their speed. It's how far they're going to get based on the amount of time that has already elapsed. So let's go ahead and graph friend number 1 over pink, the equation on the left. Oh, I did both of them. There you go. Okay, so friend number 1, which is in pink, which is already here, and I labeled it using the equation, has taken off walking, right? And that's their line. Now, friend number 2 shows up at 0 time. So even though friend number 1 has already been walking, and technically friend number 1's line actually goes on this way because they've already done some walking, we're not going to really care about it because, again, we care at the moment when friend 2 starts walking. Okay, so there is technically information that goes off of this graph because friend 1 has already been walking for a while. Okay, but friend 2 shows up, and this is what their line looks at. And again, graphing is not a precise science when you're using paper, pencil, something humanly done. And again, I will show you how to do this with a graphing calculator, or not necessarily a graphing calculator because I don't expect you to have one, but I'll show you how to use GraphSciCal to enter equations. And then basically, because most of our electronics are just huge calculators, they can actually do this and physically represent it for you. What you look at on the screen is basically a huge calculation that determines what color is going to be in each place, and then obviously pinpointing your touch and all this other stuff. It's hugely related, and it's totally awesome and whatnot, and I'm just getting a little geeky. Ignore the geekiness. Okay, so the point where both people have walked the same distance from the time when the second friend got there is actually, it's a sloppy line, yeah, but when they intersect is 6 miles. So both of them are going to get at the same point basically on the track. They're going to actually meet up on the track at 6 hours, and it's 1.5 hours after the second person got there. Okay, now again, if you were to plug this information back into both these equations where t is 1.5 and the distance is 6, or d of t is 6, you're going to get a true statement for both of these situations. So again, it's 1.5 hours after the second person got there, but you know, it's more than 1.5 hours since the first person started walking. Okay, so that's that. All right, moving on. I know this is going to be a long recording, guys. Sorry, this is new material for most of you. All right, moving on. Okay, so a system of linear equations that has no solution when the equations are parallel. What why is that? Well, if they're parallel, do they ever intersect? No, by definition, parallel lines will never hit each other. That's why they're parallel. And if you can remember the definition of parallel lines based on the slope and intercept from last chapter, you might be able to solve a few of these questions without even having to graph them if you can identify stuff. So let's talk about that real quick. So, do you notice something without even graphing? Do you notice that the slope is different, or the slope is the same, but the intercept is different? That by definition means that the equations are parallel. But let me go ahead and show you just graphically in case you didn't believe me. So let's go ahead and graph this. So there's the purple line. I started at positive 1. I went down 2 to the right 1, or down 2 to the left 1. I did this as if my lines were parallel, or positive. Oh, Miss TH, you're not paying attention. So let's just make them positive right now. And just pretend that I didn't make a mistake. Yeah, the lines actually should have been going the other direction, and I should have noticed that. But let's pretend that they were positive to begin with. Okay, so I go up 2 to the right 1, up 2 to the right 1, up 2 to the right 1, or I could go down 2 to the left 1, down 2 to the left 1. So that's the purple line there. And then label your equations, label your lines with the equations. There you go. All right, and then the orange line right there, same slope, different y-intercept. And I even made the y-intercept negative 2. Man, what's up with me today? I must not have been paying attention. I'm sorry. Hey, but at least I'm catching my mistakes. So there you go. It's easier to see with negative 2 anyway. Okay, so there you go. There's the orange line. And the lines will never meet. They're going off in their directions, and because they have the exact same slope, they're never ever going to intersect, or form an intercept. And that means that there's no solution for this system. There's no one point that both lines have in common. If I were to stick a point into one and get a true statement, I can't plug that same point into the second one and still get a true solution, or a true statement. So parallel lines, no solution, okay? All right, so let's talk about the other situation. What can you determine without graphing if there's no solution? Same slope, different y-intercept, means they're parallel. Parallel, which means no solution. There we go, no solution. Okay, now let's look at one more situation. And that is the line y equals 1/5 x plus 9. And we also have 5y plus x, 5y equals x plus 45. I grabbed the first line because it's already in slope-intercept form, and I labeled it. It's beautiful, but we need to stick the purple line, which is the bottom one, into y equals mx plus b format. So I'm going to divide by -5 on both sides, cancel out the 5 on the left, do hearts. That gives me y equals x over 5 plus 45 over 5, which simplifies down to y equals 1/5 x plus 9. Oh, that line looks so familiar. Hey, it's the exact same line. Check that out. So if I graph it, my points end up in the exact same place because they're starting in the exact same place and they have the same slope, which means exact same line. Exact same line. They are on top of each other. They are the exact same line. Same line, exact same line, which means infinite number of solutions, which means that all of those red dots are all solutions for both of these lines. If we plugged in any of those red points, we're going to get a true statement for both the blue line and the purple line. And even all of these gray ones too. Okay? So again, when the lines are on top of each other, it means that the lines are infinite number of solutions, and we just say infinite number of solutions. Okay? All right, I'm done. Sorry it was long, but hey, we had fun, right? All right, bye guys.